Okay, well, enough people are here for this talk, so we'll get started. So hopefully you've been having a great week, doing a lot of things. Just after my talk here is our poster session. So those of you who asked for posters to be printed, they're all sitting right here on the wall. Claire has all the stuff to put them up. So just after we're done with my talk, we'll take them out there, get them put up, and I'm going to walk around and find out what you all are doing. So the purpose of the talk today is to sort of build on the things you've seen in the last few days and set up the talks actually for tomorrow, okay? And so the point here is that so far you've heard a lot about sort of where the state of the art of semiconductors are today and some of the sort of the near-term challenges. And I want to take the opportunity to think about a little bit further in the future and think a little bit about what are the materials implications for that. And so before I get too much into detail, I have to thank my incredibly talented team who does most of the work that I'm going to show you. And this includes not just permanent staff for both PARADIM and our Institute for Quantum Matter, but all of my students and postdocs, both current and former. And I'll call them out individually for things that they've done. And of course, you know, in order to actually do research, you need money and funding to actually do the work. And so I'm very thankful to all of my sponsors for having provided the resources to do what we do. So first, I'd like to give you a background of a couple of semiconductor frontiers. Then I'd like to introduce this idea of quantum materials and quantum information science. Then I'd like to give an example of building a new and potentially useful device from those materials. And then if I have time, I'll talk a little bit about what the frontiers are. And this is going to be interactive. So we're going to, in a couple of minutes, I'm going to ask for your feedback. But first, I don't think anyone in this room is going to quibble with the statements that materials sort of underlie what we do in the world, right? And this is everything from the tables and chairs that you're sitting in, which are, you know, structural materials, if I were to use it that way, to, you know, to the fluorescent components that are in what are called gene chips. These are basically ways to sequence human genomes very rapidly, right? Or the superconductors that are inside MRIs, right, and provide valuable medical service. And of course, there's a long history of this, right? So of course, the transistor, which is a big subject of our talks this week. But actually equally important for the computing revolution was the development of ultra-pure silica glass, which is fiber optics, right? Because this is what has enabled incredibly long distance, incredibly high bandwidth communication, right? And that would not have been possible if people hadn't figured out basically how to melt ultra clean SiO2 on the top of a drop tower and pull literally miles of very, very low loss optical fiber. Okay? Another really important technology in optical fibers is, even though they're low loss, they're not no loss, which means the light does get lower and lower in intensity with time. So if you're going to transmit data across oceans, for example, you need amplifiers. You need things that take that weak optical signal in, okay, and regenerate it and produce a bigger signal for the next leg of the journey. Well, it turns out that erbium ion doping to make something called an erbium fiber amplifier was the critical technology to enable that, because it allows you to regenerate the optical signal without converting it to an electrical signal first. Okay. So I don't think anyone's going to quibble with this statement. Okay. I'm going the wrong way. And I already showed this, so I'm not going to talk too much about materials life cycle other than to say, obviously, you need to think about materials. Stone Age, what comes after the Stone Age? Bronze Age. And why does the Bronze Age come after the Stone Age? I mean, I just want to think about this in very gross terms. Like, okay, the Stone Age was people figured out you could hit rocks together and make sharp edges. Huh? Yeah, so the Bronze Age was, we throw these certain rocks on a fire And once the fire goes out, we have this coppery metal, right? So they learned, so you take copper sulfide minerals, and when you heat them up, they turn into copper metal, okay? Plus sulfur oxide gases. And this was born the Bronze Age, right? What comes after the Bronze Age? A little tongue in cheek here. Iron Age, okay. And so just in the same level I just described how the Bronze Age appears, how did the Iron Age appear? Anyone know? Huh? Throw a different rock, but you also had to do two other things. Well, you have to get the rock, but the good news is the rock here is rust, so that's nice and common, certain parts of the world. So you have to not only throw iron oxide on the fire, but you also have to add coal, coke, carbon. And you then have to blow on the fire to get it really hot. And if you do that, then once you let the fire go away, you find that you've got this, once you polish off all the oxide on the surface, you find out you have this wonderful silvery metal, which has a lot of attractive strength properties, and this was born in the Iron Age. And many people would argue that we're now in the Silicon Age, in part because some of the things you've seen in the workshop this week, right? That basically we have this incredible infrastructure to control the atomic structure of layers with nanometer precision across centimeters of wafer, right? That's better than 1 part in 10 to the 8th precision, right? That's really good. And not only are we doing that like in one heroic measurement, but we're doing it on every wafer as you process it through a foundry, right? And so you should think about, well, what really enabled that? Well, it was a combination of things, right? So the transistor fundamentally requires the material to be actually quite pure because you need to be able to control the dopants in order to produce the useful devices. And so actually floating zone growth, which you guys have seen, is a later variation of something called zone refinement. And zone refinement was actually the technique developed at Bell Labs that allowed them to make the germanium that was pure enough to actually show transistor behavior, okay? And a fun part of that story is Bell Labs didn't want to fund that work, so the guy did it in his free time in a broom closet. So we literally have the transistor technology today because someone at Bell Labs didn't listen to their boss and did it anyways in a closet, okay? Also, just because I know many students in the audience, including a few of mine, this is an actual page from the lab book with the first successful transistor that was made. I want you to notice the date, December 24th, 1947. So day before Christmas. I would really love to know if they all came in on Christmas Day. I actually don't know, but I have to find out at some point. So we're definitely in the Silicon Age. So here's a die shot of a modern processor, okay? It's the Apple M3. There are 92 billion transistors on this object. But now I want you to take a step back and say, wow, okay, no one person can possibly know what all 92 billion transistors do in detail, right? But we can still identify what are the main parts of this chip. So does anyone want to take a stab of want to tell me which part of the chip to point at and tell me what it is? So what are the kinds of things that are on this chip? What do you think? Wow, dead silence. Okay, I'll walk you through it. So okay, first question. Does it look uniform? Definitely not. Okay, so that means there's some structure to it, and that structure probably is associated with the different components of a modern chip, right? The different functionalities that you might associate with a modern chip. Okay, so what kind of functionality do you think is built into a chip like this? What's one thing that you think is that? Yeah. Memory. Okay, we're going to address memory in just a minute. Forget memory for a minute. Yeah, I mean, you're right. Well, no, okay. So actually, well, okay, fine. I don't care. Let's do memory. Okay, so you see all these, so there's some logic stuff here, but you see all these sort of regular patterned arrays here? That's memory. Okay, and in fact, it's actually cache, something called cache memory. We'll talk about why that is in just a minute. That's cache. Okay, so there's memory on this chip. There's more memory elsewhere. What else? That's why I wanted to defer. What else is in a modern processor? Huh? Storage, that's also off chip for our purposes. Probably some logic gates, and in particular, some CPU cores or central processing unit cores, the things that actually execute instructions like add, subtract, multiply, divide, and that kind of thing. So that's actually what each of these is. Okay? It's actually probably the block of 4 if I'm counting right. Okay, those are the CPU cores. Okay, what else? What else is on a modern chip? You need power control. Yeah, absolutely. That's actually up here. And maybe up here too. I can't tell, but certainly up here. What else? Communications. We need ways to communicate to the outside world. That's a big part of this chip. And in fact, there's 2 different kinds of communication we're going to have to the outside world. We're going to have very high-speed communication to random access memory. Okay. And then we're going to have still, on the scale of humans, blindingly fast, but comparatively not as fast, communication to other components in the system. So both these edges here, these reproducing patterns here, these are memory interface controllers. So those are the things that talk to random access memory. Okay. The top part here is decorated with some of the other interfaces. Okay. So like these look like what are called Thunderbolt ports. So basically, PCI Express is one of the common sort of standards for communication between chips, and or like you're familiar with the USB-C plug in your chip. Essentially, it's these that eventually connect to that. Okay. What else? So we've covered some chunks of the chip, but there's still a couple pretty big pieces missing. So what else is on this chip? So I guess an important thing to know is, right, this is a single chip that powers a laptop. There is no separate graphics processing unit chip. So somewhere we have to have the graphics processing unit, which looks an awful lot like logic, because it is logic. It's just logic designed to work on the sort of do the same thing to many different numbers simultaneously. Okay? And that's actually what's here in the center. Okay? And so you can see there's sort of, we could keep going, okay? But the point here is that when you have 92 billion transistors on a chip, this is about 150 square millimeters, okay? So it's not actually that big, right? You have a lot of functionality, right? At a lot of length scales. And at this length scale, which we can view optically, it's like whole units, right? And each one of these units can be many millions or billions of transistors, right? And then you have to zoom in on each of those to understand. So we're definitely in the silicon age. You already saw this in Joan's talk yesterday, or at least a version of it. But basically, over the last 50 years, we've sort of systematically shrunk the size of transistors. Okay. And up through what's called the 22 nanometer process node, the number had a physical meaning, okay? And that physical meaning is quite literally the distance between the source and the drain in the chip. So it depends, can't tell which way this is oriented. Well, you can see it here. So it's sort of like, if this is your gate, source and drain, it's this distance here, okay? Trying to orient myself. But then, when you're at 22 nanometers, you run into all kinds of problems, right? What kind of problems do you run into when you want to make patterns of things that are of order 22 nanometers in size? Huh? Atomic level defects become important, right? Because 22 nanometers is, each silicon atom is what? 2 angstroms in size, right? So a 22 nanometer length is 110 silicon atoms, right? Plus or minus 1 silicon atom, or plus or minus a different atom other than silicon. This starts to be a huge fractional change, right? What goes on? And in particular, so that's one problem, is just you become very, very sensitive to what are called stochastic effects, right? The random plus or minus 1 or 2. What's another problem when you start to make these things really small? Tunneling, indeed. So as the distance between the source and the drain gets shorter and shorter, remember, it doesn't matter how good the insulator is or the thing that you've turned insulating because you applied a gate voltage is. In the middle, it doesn't matter. The wave function still penetrates through that region. There's some probability of tunneling through it, right? And in fact, that tunneling scales exponentially with distance, which means at 22 nanometers, you might be okay. But at 10 nanometers, now your what's called leakage current is going to be really high because now you're dominated by tunneling. So this is, you heard yesterday that one of the big challenges is reducing power consumption of chips. This is the fundamental physics origin of that large power consumption in small devices, is that just by being physically in close proximity, there is quantum, even if the material is perfect, there is still a tunneling current. Okay? And that's a limit you cannot beat, as far as we know. Okay. What else? So those are definitely issues, but what else are issues when we try to make things really this small? Right. So that's a good question. So lots of people love to focus on the transistors, but the reality is, and I don't know that I have a picture of this in this particular slide deck, but there are often, but in order to connect those transistors to each other, you need to use many layers of metal, right? And in fact, actually, if you look at a modern chip, there's like the transistors down here, and then almost all the layers are the metal interconnects. And now you have to start worrying a whole lot as you make those interconnects denser and denser. You have to start worrying a whole lot about, well, when a current flows here, that generates a magnetic field, that induces a current flow in this other piece, and it becomes, as you noted, so things like crosstalk, other electrical effects, so there can be capacitive effects. So what determines the speed one of the things that determines the speed at which you can cycle something is, well, how many electrons do I physically have to put through it? Well, that depends on the capacitance. And even if you don't build a capacitor in it, you still have an intrinsic parasitic capacitance, okay? So all of those things become issues. What else? We saw a talk earlier this week on at least one of the other big challenges. Huh? Well, thermal management's a big issue, but it'll become even more of an issue in a minute. But also, how about just the patterning of these things, right? Right? Lithography itself. How does lithography work? You have a light source, you have what's called a mask, right? And you shine the light through the mask and you expose what's called a photoresist, right? There's this whole issue of like diffraction limiting, right? So if your wavelength of light is, say, a 200 nanometer excimer laser, which is something that's was commonly used for a long time and was called deep ultraviolet lithography, what's sort of the minimum structure size you can make? Well, in a single exposure, the answer is of order 100 nanometers. And it doesn't matter how much you try, you can't make it smaller than that, okay? So in fact, to get to 20, so you should start to wonder, okay, we're making things with lateral dimensions of order 22 nanometers, and we're using light that's 100 nanometers, or 200 nanometers, actually. It's the light is 200 nanometers, so your diffraction limit is 100 nanometers-ish, give or take. So how do we do it? Anyone know how this is actually done? It's a combination of things. So the first is, suppose instead of just exposing the wafer directly, suppose I immerse the wafer in water. Well, water now has a refractive index that's not 1. What does a refractive index greater than 1 do? It changes the wavelength of the light, right? So this is what's called high numerical aperture or immersion lithography. Is you manipulate the light out here with 1 refractive index of air of approximately 1, and then you send it through a material with a higher refractive index to essentially reduce the wavelength and allow you to build smaller features. Okay? The other thing you do is something called multi-patterning. You could have a whole school on multi-patterning, but the basic idea is, suppose instead of doing a single exposure, suppose I do multiple exposures with different masks. And suppose I've chosen the masks so that when I look at the sum of the intensities across all the exposures, the resultant net light field has larger peaks, in particular in very narrow places. So think of, if you're familiar with like Fourier summing, this is kind of what you're doing here, right? You're basically saying, well, if I shift the, if I have a thing that's wavelength limited there and it's like this, but then I phase shift it by 10 degrees and it's over here, the place where they overlap the most can be a lot smaller than the wavelength of the light. And this is another way to beat the diffraction. Okay. And then it's only recently that the solution has been to use a shorter wavelength of light in the exposure. And this is EUV, or extreme ultraviolet lithography, where the incident wavelength of light is of order 20 nanometers. Okay. So now you no longer have to play all those games I just mentioned. Okay. But you need an EUV light source, which, as you heard, is a non-trivial thing, as it turns out. Okay. So what's happened below 22 nanometers is we've had to change the geometry to avoid like the tunneling issues that we just mentioned, right? So the different companies call it by different names. Intel calls it a FinFET. What's the idea? So yeah, this is probably the good one. So let's just take, excuse me. So in the simplest instantiation, you can have a source, you can have a drain, okay? And then what happens is then you wrap the gate around these fins, hence the name FinFET, okay? And why do you do that? You do that because you still keep, there's still, these things are still 20 nanometers high, so you haven't shrunk the dimension in any meaningful way, okay? This is still of order 20 nanometers. But now what you've done is you've wrapped the gate all the way around the channel, okay? And so you're able to avoid crosstalk between the gate and the source and the drain, okay? And shrink it in this one dimension because it's 20 nanometers, but it's no longer 20 nanometers flat, it's 20 nanometer pillar, okay? And then, of course, you saw the more modern version, the most sort of the current state of the art for this, which is what's used for what's called 2 nanometers. Now, keep in mind, 2 nanometers, the transistors are all still of order 20 nanometers. That hasn't changed in a decade. What's changed is you're building them in, you're able to pack them more tightly, and so it's become a marketing term, okay? Well, if you were to do it in the old planar way, how big would the transistors have to be to pack them that tight? Okay, and this is what's called gate-all-around transistors, as you can see here. There was a question earlier this week about, what's the relationship of this between this and nanomaterials? Well, all these things are already heavily nanomaterials, right? I mean, this active channel material here, right? It's 5 nanometers by 40 nanometers here. This is a 2 nanometer process. Okay. Well, that already looks like a nanosheet to me, right? And in fact, if you continue to make it thinner and a little bit narrower in this dimension, that starts to look like nanowires, right? So all these things are already highly nano. So this is all well in progress. A good thing to remember is that, this is sort of, well, I mean, this was back when IBM did it for the first time, but the TSMC version of this is producing chips now. The things for the next sort of 3 or 4 years in this domain, that they're already worked out, okay? Well, worked out. They've already been done in small production batches, okay? And it's more of the same. The problem, of course, is, as I showed you, is this is quickly running out of steam, okay? I mean, this is essentially becoming incredibly more complicated, incredibly quickly. And so Moore's Law came up. So there are different versions of Moore's Law, right? So the Moore's Law that's sort of often quoted is what? The number of transistors on a chip, on a given area of a chip, doubles every 18 months, right? Right? But that's actually not what original Moore's Law was. Original Moore's Law was the cost per transistor goes down by a factor of 2 every 18 months. And so if your manufacturing process is more or less a constant, then those two numbers are actually the same, mean the same thing, right? Well, we have now entered the age where building a single gate all-around transistor is more expensive than building a single FinFET. So even though you can build more on a chip, the cost per transistor has actually started to go up now. Okay, so this is where it's sort of really started to reach the end of scaling. And so really the only way to continue scaling is to go three-dimensional. Okay, so here's an example of an actual three-dimensional thing you can go buy off the shelf today. So all of you are familiar with flash memory. Okay, almost all flash memory that you're familiar with is actually what's called NAND flash or not and flash. It's where the storage is based on what's called a not and gate. Okay, this isn't a logic class, so I'm not going to run through how that works. I'll just say that that's the basic element. But the cool thing about not and gates is they suck no power, right? They're non-volatile. This is what makes them useful, right? You can unplug a flash drive, it has no power, and it still remembers the information, right? Okay. And it's also, every memory bit looks exactly the same. It's not like a logic device where I need some complexity to learn how to do multiplication or something, right? Each bit looks exactly the same. So it's very like, yeah, same thing, copy pasted a million times, billion times, trillion times. Okay. So here's how you do it in 3D, right? Why don't I just build a layer of NAND gate memory, build another layer of NAND gate memory, another layer, and they just stack them up layer by layer by layer and have these what are called through silicon vias. So basically, ways to get the information from down here up to there, where I can now go build all my metal layers and actually connect everything. Okay. And so a modern NAND flash chip has of order 256 layers. Okay. I want you to remember that because there's a question I'm going to have for you in just a minute. But you're not limited to stacking just memory, right? And in fact, you could imagine, more than imagine, you can go buy chips today that do this, okay? I can make a silicon chip, do all the lithography on it to have all the different components. And then if I can find a clever way, and I can do that for another chip, and I can do that for a third chip. And now if I can find a way to stack those chips on top of each other and connect them electrically, now I can start to build in 3 dimensions by basically making 2-dimensional objects and then, well, stacking them. And so going back to the Apple M3, just to pick a specific example, what I showed you was the compute die. Stacked right on top of it is actually the random access memory die. Okay? And so how these are actually connected, because remember, you've got nanometer size objects across individual chips are of order square centimeters. Okay? And now I'm going to position these two and let them talk to each other. What precision do I need in aligning a centimeter scale object with another centimeter scale object, right? This is insanely precise positioning, right? But it's actually worse than that because now I actually need good electrical contact between the layers. And if I just physically put the two together, I'm not going to have good electrical contact, right? So you play very complicated games where you like make holes with standard lithography techniques, connect them, and then do another metal deposition process to fill in the holes. I'm simplifying greatly, okay, but that's the idea. And that's how you connect them. Okay, the idea here is to go 3-dimensional. But now I have a question. What are the challenges here? So this one seems pretty obvious. You need all processes for adding the next layer to not destroy the previous layers, right? It does me no good to be able to build layer 3 if in the process I destroy layer 2 underneath, right? And now think about just how hard that is from a materials perspective, right? Because these objects are nanometer in scale. How long or how hot or how whatever do you need for atoms at the nanometer scale to diffuse with each other? Not long at all, right? So this starts to put you very quickly in a box where it's like, well, I may know how to do it, but I can't practically do it because as soon as I do, my previous layer just loses all of its nanoscale structure and diffuses into itself. Okay. And so in practice, not entirely, but the main way this is currently handled is actually through the stacking of different dies, this process I just described to you. And here's, oops, there should have been an image here. At some point, an image here will show up showing you what that actually looks like. Okay, But the total systematic, but now if I'm going to do this not just for 2 layers or 3 layers, but 128 or 256 or a million layers, now my total positioning error across these has to be really small, right? And it's not just, it's not just, well, this is a rigid object and this is a rigid object. No, no, no. It's a centimeter scale object, right? It's not atomically flat over a centimeter, right? This starts to become a real challenge, as you saw in some of our earlier talks. But there's a more fundamental challenge in going to 3 dimensions. And it has to do with the fact that it's the first time you're really changing the surface area to volume ratio, right? Everything that's sort of done in the plane, it can be many metal layers and things like that, but it's still approximately a 2-dimensional object. The aspect ratio of the overall object is still really long here and really short here, okay? But now, if you're really going to build things in 3D, you're now going to have a dramatic reduction in the surface area to volume ratio because you're adding a lot of volume without adding a lot of surface area. Is that a problem? Well, it is a problem, okay? How do we get enough power in, right? How do we get our signals out from layers buried in the middle? How do we get the heat out? So I just, showed you a modern chip. What's the emitted power density from a logic chip? Does anyone have a sense of the scale here? Just like if I look at a modern high-end, data center CPU or GPU, how much energy per square area is being generated in the form of heat is being generated from the operation of that chip? It's roughly the same energy density as a rocket engine. Okay? Right? And so now, and in 2 dimensions, we can deal with that. Because if it's a 2-dimensional chip, all we do is we slap a gigantic, large thermal mass with a high thermal conductivity, aka a piece of copper or tungsten or some variation thereof on the top, and basically let the copper and the tungsten absorb all that heat and take it away from the chip. Okay? But now, if we're going to go to 3 dimensions, this becomes not so doable, right? Because again, it's surface area to volume ratio, right? Well, now I'm going to, if I stack 1 million of these, I might only double the surface area, but I've increased the power I have to get rid of by a factor of 1 million. How's that going to work, right? This problem, in a nutshell, is why the current sort of stacking of chips is done comparatively with large numbers for memory, for flash memory. So 256 of more than that now, but of order 256, okay? Whereas for logic, the absolute state of the art is a logic chip here and a logic chip there. And then you're cooling it from both sides, okay? No one knows how to get the heat out. No one. And because of that, it's this last area where novel materials are actually likely to have the biggest impact, because it's a problem that we just don't know how to solve with any existing material. You may have seen some of those thermal conductivity of the various materials that were being quoted. None of those thermal conductivities are very big, right? The thermal conductivity of copper is, 400 watts per whatever in the units you saw earlier versus, 2 for silicon. Okay? So no one knows how to get the heat out. And so there are some pretty, okay, there's the image for earlier. There are some pretty crazy ideas of how to do this. Like, well, maybe I put a layer of logic, and then I put a layer that's just like little nano channels that are, 20 nanometers by 5 nanometers high, then the next layer of logic, so on and so forth. And then I use high pressure water, at 1,000 PSI to get it through such tiny holes, okay, that are long and narrow. And maybe I then flow water through these channels to be able to dissipate the heat. That's sort of where we are in the thinking of how to tackle this problem, right? It's insane, okay? Maybe you could do active heat extraction, right? So maybe instead of channels where you're trying to flow water, maybe you put yet another thing that maybe generates some heat, but in the process allows you to move that heat outward to a place where you can then deal with it better. right? Maybe you can be even more clever and actually craft the phonon. Phonons are just lattice vibrations. Craft the phonon band structure of these channels or otherwise to make it so that when heat's generated in the middle, it just wants to flow out through the channels. Okay? All of these things are being worked on. The point is, it's a hard problem. Now, this image is the stacking of dyes. So you're basically seeing each substrate, 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 substrate. Got to count the right number there. And then the point is, you have actual circuits, and then of course you have these through silicon vias that I was describing, right? This process, by the way, of doing the stacking, right? That's not really scalable. Well, I mean, it's scalable to hundreds, maybe thousands. But do you really think we're going to start, stacking millions? I'm not likely. Okay. So there's also sort of an untapped question of how do you really go to 3D? Okay. So questions on that. I spent way longer on that than I wanted to, but hopefully it was useful. Yeah.
When you talk about channels and
yes.
Out
yeah.
Like, I guess a limit on how much stuff on the outside you have dealing with it. Does that like?
This is the surface area to volume ratio conundrum, right? That if you have similar power losses to what you have in logic devices today, if you do stack 1 million of them together, you now have 1 million times the heat, and you've only increased the surface area by a factor of 2, which means, okay, even if I can make the channel a magical channel material that magically channels all of the heat from inside to the surfaces, those individual surfaces are now 500,000 times the energy density of a rocket nozzle engine, right? And I somehow have to actually cool that. And it's not clear how to do that either, okay? So there are some people who I think are right, actually, that this isn't going to work at the end. Well, as in it'll work of order hundreds, but it won't work of order beyond that, okay? And that in order to fix this, we're going to have to do something. So a really simple option is, if I'm going to build in 3D, why don't I just make the logic units bigger again? Because remember, the bigger they are, the less tunneling you have, the less impact of stochastic effects, right? So actually, the more off transistors are when they're off. In other words, the less heat you actually generate, okay? So one simple option would be to say, well, why don't we just go back to transistors that are 50 nanometers in size? I mean, that's still insanely small, but 50 nanometers in size, right? But do so because off is really off. And because of CMOS processing, you only actually lose. If your transistors really are off when they're off, you only generate heat when you switch, okay? So that would be an option, right? And actually, that's sort of what happened with flash memory. So if you look at flash memory, it got smaller and smaller in plane, but then it became lossier and lossier. Okay, so basically individual bits became much more likely to flip. Okay, so there were more elaborate error correction mechanisms to deal with that. But then once the stacking of the layers of the chips became popular, they actually made the NAND flash cells bigger again. Because they basically said, well, now I can stack lots of layers, so I will pay a price in any one layer, because now it makes the stacking much easier. Maybe we can do the same thing with logic, but actually, if you run through the numbers, a factor of 1 million is a pretty hard thing to cut down, okay? So, other questions? Yeah. Right. But what you have control over is if you change both the material that a channel is made of as well as the dimensions of the channel, you have control over the energy momentum relationship of those phonons. And so it becomes a matching problem. So a way to think about this is, if you're familiar with what's called a waveguide. So this is, or it's like what a fiber optic does, right? That basically, like, the fiber optic has what's called total internal reflection, right? That as long as light coming in within some angle range, every time it hits a surface, it's 100% reflection. You can do the same thing anytime you have an interface with a phonon. Think of a phonon as sort of this it's not a propagating light wave, but think of it like one. Every time it hits an interface, it has some probability of transmitting and some probability of reflecting. Okay? You can, if you choose your things right, you can make sure that most of the energy is being dumped into particular phonons that propagate in a particular direction such that the reflectivity is 100%. At least that's the, is this really done in practice? No. Are there select examples of this idea being maybe possible? Yes. Other questions? Okay. The other frontier where materials is likely to have a big impact is beyond sort of classical computing. Okay, you already heard about, well, you heard the words neuromorphic computing from Stuart Parkin. The idea here is basically to go back to essentially analog circuitry, okay, instead of sort of digital ones and zeros, but go back to a more analog model, really slow down the clock rate, but as a result, allow you to do operations much more effectively, right? Your brain does in 100 watts what it takes a data center, 10 megawatts or more to do. Okay. The other regime is just to completely change how you do computing. So this is a picture. You've probably seen some version of this at some place of a quantum computer. And I always laugh as a physicist because what is this mostly a picture of? Cooling. It's mostly a picture of a dilution refrigerator. Right? Here's a nice plate. There's another plate up there, right? As the stages of a dilution, what's called the dilution refrigerator, which is the way you actually get to a very low temperature. And all of these are actually microwave signal wires. Okay. The actual superconducting quantum chip in this is this little thing here. A tiny little thing there. Okay. And that chip is actually, compared to everything I just showed you from a CMOS perspective, an incredibly simple chip. The features are of order microns in size, okay? There's no, millions of metal layers or anything like this. And it's just built out of a superconducting material. There are a couple elements in here that are, this is still a very complicated device, but compared to what I was just showing you, it is a ridiculously simple device, if that makes any sense. Okay. And so, that's the actual quantum bits, and the rest is how you interface with it. And so, in fact, Intel and others have invested a lot of money in trying to understand, can I build cryogenic microwave circuits? Because the reason for all of these microwave pipes, that's what they are, they're microwave pipes, okay, is you do a rather silly thing. Your chip is operating at 0.02 Kelvin, so very close to absolute zero. But then in order to do operations, you need to use microwaves, okay? We have lots of really good room temperature microwave circuitry. So what you do is you literally take the microwaves from here, send it out the cryostat to room temperature, to microwave circuitry at room temperature, do the microwave stuff at room temperature, and then send the microwaves back into the quantum machine. If that sounds horribly inefficient and challenging and difficult and limiting scaling-wise, you'd be right. And so if you sort of look at sort of every generation of quantum computer that exists so far, you'll notice that the dilution refrigerator gets bigger. More microwave pipes show up, and that's really the limit in this. And in this very interesting thing, right, is it's like, well, the chip's an important part, but actually it's the non-qubit part that's the challenge here. How do I get rid of all that? Okay. Superconducting circuits, and I'm going to show you an example of something about this in a minute, are good for quantum computing, but they actually could be useful for just normal computing if you're willing to cool the device in some kind of refrigerator, okay? Because there's zero loss, right? So you might be willing to pay the energy cost to cool a chip in return for having a chip that then during operation doesn't generate heat, right? So this goes back to the heat management problem I was telling you about. If your circuits aren't generating any loss, then sure, I can stack them in 3D. I can do whatever I want, right? And I might be more than willing to pay the price to somehow cool a chip, such a chip, in return for it not being a rocket engine on steroids, okay? And of course, there's lots of materials challenges in all of this. And it's also the place where it's most likely for new materials to have an impact because there's no competition. You saw with beta gallium oxide, the beta gallium oxide talks, right? You saw with the, when I mentioned GeO2, rutile GeO2, right? These are, or silicon carbide, these ultra wide bandgap semiconductors, right? They're trying to attack a market. But in every single one of those talks, what was the competition? Silicon, right? And it's like, well, how do you beat silicon for what you're doing, right? That means that you're being put in a smaller and smaller box in terms of where you can have an impact with a material. This is a new frontier. Neuromorphic computing is a new frontier. They're really, I mean, you have very little way to speak of in terms of competition, right? So you're more likely to have the opportunity to inject new materials and make an impact. Questions on that? And there's no way I'm getting through the rest of this. So at the rate I'm going here. So maybe I'll just say what comes after the silicon age. That's really the question quantum materials is trying to address. This may be too old, but did any of you participate in this? This was a Reddit experiment. You remember seeing it? Okay. So what was the idea? The idea is this is 1024 pixels by 1024 pixels. And the rule was anyone on Reddit could go and change the color of 1 pixel in the image, and they could change like the color of 1 pixel every 1 minute. Get millions of participants from around the world, and all of this beautiful structure emerges. Okay? That's an example of collective behavior. It turns out that you don't need a lot of complexity in the individual interactions to generate collective behavior. The flocking of birds is another example. Birds want to get close to each other to allow for drafting, so reduced energy consumption during flight. But they don't want to get too close because otherwise they crash into each other, and that's not good for either bird, right? So two very simple interactions, one attractive, one repulsive. And then you get flocking behavior. Okay? Electrons in solids do the same thing. Electrons are attracted to nuclei, repelled by each other. Very simple interactions. But when you put 10 to the 23rd electrons together, now they can do all kinds of crazy things. And that's the idea behind quantum materials. So I'm just going to skip most of this and basically just say, this leads to questions. So unlike, so for like beta gallium oxide, right? I can describe how electrons in beta gallium oxide behave very, very well, okay? Using a very simple toy physics model, where basically I replace the electron with an electron that has a different mass. And if I'm going to consider its whole transport, I flip the sign of the charge and I change its mass. And then it otherwise behaves like a nearly free electron gas. Okay? That's not true for many of these quantum materials. Okay? So you end up having to ask the question, can some of these collective behaviors be used to radically modulate some of these other properties? Superconductivity is a salient example. You wouldn't expect to be able to have a material that has no resistive loss. And yet, due to the collective motion of electrons in a superconductor, you do. And I think we've just scratched the surface of what's possible there. Again, I'm going to skip all this. I want to just point out with quantum information science, you know, these are starting to look like chips, right? Comparatively simple chips, but chips nonetheless, right? But what's interesting about these chips is now we're having to incorporate new materials that haven't been incorporated before. And so you're going to hear a talk tomorrow by some of the folks who work with IBM to figure out how to incorporate the superconducting materials for superconducting qubits into a scalable foundry process. Okay? I'm going to skip all this because I want to get to one example of a quantum material doing something interesting with the device. So to introduce this idea, I need to tell you about this thing called a quantum spin liquid. So a quantum spin liquid is a funny idea. Each blue dot here is an atom. Each atom has a spin, or has an electron, excuse me, has an unpaired electron. That electron has a spin. In other words, it looks like a little mini bar magnet. Most material, if at high temperature, those spins fluctuate. This means I have entropy. I have a lot of entropy because there's a lot of different microstates. Okay. Thermodynamics says that as I cool the system off towards 0 Kelvin, that entropy should go away, right? This is the third law of thermodynamics. Usually, that entropy goes away by forming magnetic order. You get all the spins point the same way. That's a ferromagnet. It's like your fridge magnet. Or they point opposite ways. That's an antiferromagnet. That's like the ruthenium exchange layer that Stuart Parkin mentioned earlier this week. Okay? The point is you pick an order. Okay? A quantum spin liquid chooses a very unusual kind of order, because it's an order that I can't write down in terms of this spin points that way and this spin points that way. I can't write it down that way. I have to write it down as a linear combination of snapshots where the spins are pointed in all different directions. So it's a single quantum state. So that's how I get rid of the entropy. So it's a single quantum state. But if I project it onto single spins, each spin looks like it's fluctuating. Hence the name quantum spin liquid. Okay. These, what that means in physically, what that means, this fact that it's a single linear combination that is the single quantum state. That means that that even though if I look at individual spins, they look like they're fluctuating. When I look at pairs of spins, there's correlations in their behavior. And in fact, it's entanglement. Okay. That's interesting because what that means is if I have a quantum spin liquid and I fiddle with a spin on one end of the material, due to the entanglement, that'll show up at the other end of the material, right? This will do the spooky axiom of distance thing. Okay. There are actually proposals for how you can use this to actually build quantum computers that are robust to noise, okay, which is sort of really would be a big deal if you could do it. But there are not so minor challenges with quantum spin liquids. How do you make one? And once you've made one, how do you know that you have one? Actually interfacing with spins like I just described is of itself a non-trivial problem. Again, I'm just trying to, interest of time here, I'll just say, so my group for a long time has worked on in this field. We've made various materials. One of these materials is this, the formula is not on here, niobium halides. It's a layered van der Waals material, but within each layer, it has a pattern of unpaired spins that's in the right geometry to potentially be a quantum spin liquid. But all of that isn't the really cool thing that came out of it. The cool thing that came out of it was to ask, well, as I make it thinner and thinner, what happens? So this is an interesting thought experiment. And you've already seen both cases in the talks this week. So one possibility is, as I make it, so is graphite to graphene. Graphite is an insulator with a band gap of some fraction of an electron volt. As you make it thinner and thinner, that band gap gets smaller and smaller until you make a single layer where we then call it graphene. And it's a semi-metal. It actually has a really tiny spin orbit gap, but whatever. It's essentially a semi-metal. Okay. So one general scaling law is as I break things thinner and thinner, the band gap gets smaller. The other general behavior, which is the more common behavior, and this happens for like MOS2, is as I peel them apart, the band gap gets bigger. Because basically there's less coupling of the electrons between layers, therefore there's less bandwidth, and therefore the gap between the valence band and the conduction band gets bigger. Okay. So you working with folks at Max Planck Hall, actually with Stuart Parkin's team, we took this niobium halide material and made it thinner and thinner. So we started with things that are, 280 micron in thickness, and we went all the way down to sort of 8 nanometer with a hexagonal boron nitride coat. Okay. And it behaves what I'm going to call graphene-like, okay, which is to say its gap gets smaller and smaller and smaller. That's very cool, and so that motivated a lot of work to try to make these really small, okay? And so then that led to a discovery. So there's another layered van der Waals material, niobium diselenide, NBSE2, which is a superconductor, okay, at low temperatures. And because one of the ways to interface with the spins in a quantum spin liquid involves building what's called a Josephson junction, which is basically a superconductor insulator superconductor junction, okay, we wanted to build one with this quantum spin liquid candidate material in the middle. And we did. And what you observe when you do that is what's called rectification behavior, right? So these are IV curves, but you'll notice it's asymmetric, right? This distance isn't that distance, right? It's asymmetric. So what this means is that supercurrent can flow one way, but not the other. Okay? So this is a diode. So this superconductor insulator superconductor behaves like a diode, only it's not a diode for, well, it is a diode for current, but it's a diode specifically for supercurrents. So the zero resistance current that flows in a superconductor. And to be able to do that without applying electric fields or magnetic fields or anything like that, turns out it had never been done before, okay? Now, for those of you who know a little physics, the reason for this is totally boring, okay? And it basically comes down to the following totally boring, that's the wrong words. In retrospect, it makes perfect sense, okay? Almost every analysis of a Josephson junction like this, assumption one was always there's a mirror plane in the middle. The individual layers of this material are ferroelectric. They have a polar moment, okay? So that assumption is violated. And as soon as you no longer have the symmetry that makes the two halves equal, okay, it's now possible to have an asymmetry in the behavior, okay? So it actually comes about not because of anything quantum spin liquidy here, but because the geometry of such a material forces each layer to have a net electric field, to be polar, okay? And that very strongly then has a huge impact on what happens inside this junction, okay? That citation's old, it's in Nature somewhere. You can go find it if you're interested. So I think I'm going to mostly leave it there and just, okay, so some of you did some fib semming yesterday, right? So you know that with fib semming, you can start to take some of these materials and build devices in which you can do measurements of one kind or another, okay? And so we do a lot of that. And I think I'm going to skip most of this and just leave you with some pictures of some of the things we do here and any last questions. So, questions? Anyone have questions? Come on, someone's got it. Yeah. Yeah.
They have the same restriction to, like, do they need to be as scalable as when we talk about silicon?
So that's a good question. So the question was, do materials for quantum computing need to be as scalable as the materials for silicon? Well, no and yes. In the sense of, there aren't that many quantum computers in the world right now today, and the number that do things that you truly cannot do on a classical computer is vanishingly small. Which is to say there's no current sort of real deployment of them. That's a good thing in the sense of it means initially the materials don't have to be scalable because you just need to be able to make of order 1,000-ish, of order thousands of something, not millions, in order to have a big impact. But the answer is yes, because if you really want that technology to have a broad worldwide impact, at some point you have to make it on a large scale. But I'm going to make an analogy to silicon. So when the first silicon transistors were built, silicon was more expensive than gold. That's an insane thing to think about today, right? But buying pure silicon was more expensive per gram than gold. Not because of any intrinsic scaling issue, but because there wasn't a reason to figure out how to do the scaling. And so that's my message is if one's going to disregard something because you say, well, it's not scalable, you've got to be careful because a lot of times things that look not scalable, they're just not scalable because there hasn't been a reason to figure out how to do it, right? Whereas, for example, if I'm going to start building all of our structural materials out of 100% rhenium, barring us mining asteroids that have a lot of rhenium or something, this is going to be a problem, right? So that's the distinction. So the answer is the materials need to be selected so that there is no fundamental hard constraint on them being scaled, which is different than just saying, oh, it's too expensive or, oh, we don't know how to do it at this time. It has to be, there's some fundamental thing that basically says if the world works the way we think it does, it is not going to be possible. Make sense? Okay, other questions? Yeah, and then.
So like, when you try to choose like for things to define,
Yeah.
Set a particular switch. Like, so for example, I also use like programming molecules
That's a good question. So the question is related to what makes up a quantum material. What do you need to make a quantum material? There are absolutely quantum materials based out of organic molecules. Okay. Oftentimes they're what are called stable radical molecules. So each molecule has an unpaired electron, which then becomes sort of the fundamental unit. There is no restriction in any sense like that of it's about the collective behavior, right? And so there's actually lots of places where one can get collective behavior that's not crystalline materials. I showed some crystalline material examples, but it's by no means limited to that. Yeah.
So how artificial intelligence how to run this experiment in further part?
I'm sorry, say that again. I just didn't understand the question.
Simulations.
Yes. Simulations. So that's a good question. So the question has to do with how do we use simulation to guide what we do? And there are multiple ways in which we do that. So one way in which we do that is we use it to guide materials selection. So even though the modeling of collective behavior is in general a hard problem, that doesn't mean that by using that we can't gain useful information from what we are able to do, calculation. Okay, so for example, there's a very simple form of density functional theory called just LDA with a very simple basis set. There are lots of things that gets wrong, so to speak, but it captures, but it is still very informative because it still guides you to the places where you then, you also have the other ingredients that give rise to the correlations, and therefore it. So that's one place we use it all the time, okay? Another place we use it all the time is in understanding the conditions under which to grow a material, okay? Now, this is mostly derived from a combination of theory and simulation and analytical analysis of previous experimental work. So what I mean by that is there are laws of thermodynamics. There are things like Gibbs phase rules. This puts limits on what phase diagrams can look like. So using what is known, you can back out some constraints on what's possible. If you want to see a recent example of that, you guys know we have these high pressure systems here that go to high pressure oxygen. We had a former summer student who built a tool that anyone can go and use now, which actually computes the pressure dependence stabilization energy of a set of oxides, and thus allows you to be predictive of what oxygen pressure do I need to make a particular material. It won't be, it's not quantitatively accurate, but that's not the point. It just needs to be qualitatively accurate, okay? There are more, I could go on, but hopefully that gives you a flavor. Okay. Yep. Okay, what are the Zoom questions? Okay. Okay, hold on. Let me look. Okay, so there's two questions. The first question is what's actually going on in this photo here? And what's going on here is this is actually what's called a laser pedestal growth. So the floating zone growth, which is what you can sort of see here, you have the solid material, and a liquid in the middle, right? And the liquid is held in place by its own surface tension. Now, I think as some of you have found out, it can be very hard to keep that liquid sort of stable in the zone because it really is just its own surface tension and adherence to itself that's leaving it there, right? So, so there's another form of crystal growth called Czochralski crystal growth. And this is actually how most laser materials are made for lasers. It's actually how a lot of silicon is made, okay, for electronics, which is you have a big pot and you melt the material in the big pot. You come in with a little single crystal seed on top. There's that temperature gradient now in this direction, right? Because it's hot here, and as you go up that way, it's cold. So at some point, there will be a solid liquid interface. And if you now pull out slowly at that solid liquid interface, you precipitate new material. This is called a Czochralski growth, okay? The laser pedestal growth is a mixture of floating zone and Czochralski. It's a Czochralski-like pulling, which has the advantage of, you can sort of see it's basically just a bulb of liquid with something on top. So you no longer have the stability issues that you have with a normal floating zone, okay? But you don't have a giant molten pot on the bottom. You've just melted a small fraction of it, okay? And the reason for that, the reason this is now powerful is this means in principle, you can grow much higher melting materials, right? Because if you think about how much power is required, in Czochralski, I need to melt the whole pot. Here, I just need to melt a tiny bit, right? So you can grow materials that have higher melting points. You can also grow materials that are otherwise too volatile. The other problem with melting a big pot is there's lots of vaporization, okay? Well, if I only melt a small piece of it, I limit the amount of vaporization. Okay? And so laser pedestal has actually been a very popular choice amongst our users in PARADIM because it sort of gets the best of both worlds. The other question is, how do materials apply to space? That's a whole nother lecture. I will just say microelectronics, to bring it to microelectronics. Microelectronics in space presents some interesting challenges because you're in a high radiation environment, okay? So there are these things called single event upsets, which basically proton or neutron comes whizzing through your device at high energy and happens to collide with an atom and delivers a huge amount of energy in a small volume. And even if it doesn't do permanent damage, which it often won't, it'll still flip the bit state or it'll latch up the logic. So transistors are meant to flip and sometimes it'll latch it into an on state. Okay, these are called single event upsets. They are the primary, that kind of thing is the primary thing you have to deal with when you take things to space, okay, from a microelectronics perspective. Now, size matters here, right? Because as I make things smaller, you're much more likely to get a single event upset because you need less energy deposited to cause a flip. So actually, most spaceborne electronics are still on what I'm going to call very old process nodes for one reason. It makes them more robust to the influx of radiation that you experience in space. Okay. If you could find some magical material that has no cross-section for absorption of protons and neutrons, which are the main flux that you worry about in space, now you can build all kinds of more interesting electronics, okay? Or if you could, so silicon is not so good a choice, but if you could make, for example, a substrate containing boron, boron's a really good neutron shield. So you could actually imagine that you can start to build electronics that do pick up more resistance because of their components. But that's a whole nother lecture. So, okay. So I think it's time for us to get to the poster session. Get your posters up.